Okay, so using this computer display here and this sound sensor, which is basically a little microphone, we're going to use the guitar to make some sounds of different frequencies by plucking the strings of different lengths on the guitar and seeing what kind of frequencies you get. So starting with this low E string down here, I'm just going to strike and I'm just going to hear the sound it makes, right? So that's the note E, apparently. Assuming my guitar was properly tuned, which I think it was. Now we're going to use the computer to try and capture that sound using the sound sensor. So I'm just going to hold the sound sensor near the guitar while I strike the note. And we're going to record that data here. So let's start the data acquisition. All right. Alright, that's enough. Now while that was running, you can probably see on the screen here these little red wedges appearing. So as the sound came, it started out very loud and then it died away very slowly. I plugged it again, it started out with this big wedge and then it died away very slowly. And the same again. So if I zoom in a little bit with the camera so you can see that better, here's the sound starting out, dying away, starting out a new note, dying away, starting a new note, dying away. So if we pick this whole thing and zoom in on it, we'll be actually able to see the individual sound waves themselves, because remember the computer is sampling something like 20,000 times a second. So we should be able to do that. So that's what I'm going to now do. I'm going to zoom in on this scale here. At the sound wave, we can now see it as this little succession of peaks and troughs. The intensity goes up, goes down, goes up, goes down, goes up, goes down. So this is literally the individual sound wave as it comes in through the microphone. So this thing here being measured here, voltage, you can measure actually the pressure on the sound sensor. So there's a positive pressure when the sound wave starts to come in. And as the trailing part of the sound wave comes through, it actually sucks on the microphone diaphragm a little bit, and it pushes again, pulls a little, and so on. So this is the pressure reading essentially in the microphone. And it comes out as a voltage. So we're actually seeing the up and down, up and down, up and down as the sound wave propagates through. So we can actually measure the distance between, say, two peaks on this diagram here. Much for that. Now it turns out the computer can do that in a much more sophisticated way. It can do that for every possible pair of peaks in there and then produce a graph that shows us what frequencies were actually present. Maybe there was more than one. And that's called a Fourier transform. So we're now going to try and do that. What frequencies do we actually see in here? Well, there's a lot of different peaks, and these peaks represent the different frequencies in the sound. So we can see there's a strong one here at 160 hertz, and there's also a peak here at 80 hertz. Now, if you were to go and look on the internet or somewhere and find out what is the frequency of the low E on a guitar, it should be about 80 hertz. So we see this peak, this is the 80 hertz. We see this one, which is 160 hertz, which is 2 times 80. It's called the harmonic. And then we see another one here at about 240, which is, of course, 3 times. And if we look up, we don't see another one up there, but we made it if we have more sensitive equipment. Now what about down here? What do we see down here at the low end? Well, the biggest peak in the spectrum is at 60 hertz. Now 60 hertz is a big red flag anytime you do an experiment, because it's the frequency of the alternating current that is in your house. So anytime you walk near electric wires, your body feels an electromagnetic field with a frequency of about 60 hertz, 60 cycles per second. So that's what this sensitive equipment is picking up, and so these features down here are probably also related to that. Okay, so we've shown that this string oscillates at about 80 hertz. That's called the fundamental frequency. Now, what would happen, what indeed would happen, if we were to, instead of striking the whole E string, which gave us 80 hertz, what if we strike the string at half its length? So instead of getting the whole string, what if I put my finger along it exactly the halfway point, okay? So halfway along the string is right here. Right, we could measure it with a tape measure if we had one, but conveniently makers of guitars have all marked their guitars, so right here is the halfway point. So if I strike the string there, hear another note, right? There's something that people think sounds the same about those two notes, and in fact, they're both the note E, but evidently they're not the same note, right? They don't sound exactly the same, they're different. One is higher than the other. So what is this E-ness about this note? What makes it E, other than somebody said it is? Why are these two notes E? Why is this other note not? Right? That's a different note. So we're going to look at that. So now let's play this note and capture it on the computer and see what frequency we get that time. Okay, so that has given us the green points on there, if you can see them. So I struck the string and I got these sounds that start out loud and then get quiet, again just like before. And we're now going to grab that data, put it into the Fourier transform and see what frequencies are actually present. Just like before, we've got 160 hertz. Now remember 160 hertz, I told you before, was 2 times the frequency of E. And now, when we struck the same string but half the length, that is the strongest frequency, and it's also the lowest frequency that we get, 160 hertz. So apparently, going from low E to the next E up, we simply doubled the frequency when we halved the length of the string. So that's the important part of physics to take away from this.